Hello, in this lecture we'll answer two questions. In the first question we'll find out the radius of this circle that is described by triangle ABC. In the second question we'll find out the area of rectangle ABCD that blocks this circle. We start with the first question. In the drawing we have triangle ABC, side BC equals to 2 units, angle ABC equals to 60 degrees, angle ACB equals to 75 degrees, and our mission is to find out the radius of this circle that is described by triangle ABC. We start with the first method. Here from point C we draw perpendicular on AB. So this angle equals to 90 degrees, and this angle is also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB is D. So here we created a right triangle DBC. I will copy the right triangle DBC in a new page and we'll analyze triangle DBC. Okay. So this is the right triangle DBC that I copied from the original drawing. We know that the sum of the angles inside triangle DBC must be equal to 180 degrees. So which angles we have inside triangle DBC, the right triangle DBC? We have this angle that is equal to 90 degrees plus this angle that is equal to 60 degrees plus this angle that will define as angle X. In total, the sum of those three angles must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. 90 degrees plus 60 degrees is 150 degrees plus angle X must be equal to 180 degrees. Here we subtract 150 degrees from this equation and we get that the missing angle X equals to 180 degrees minus 150 degrees, it is equal to 30 degrees. So this angle X equals to 30 degrees. You can write here that angle X equals to 30 degrees. We continue to focus on the right triangle DBC. In the right triangle, triangle DBC. It is very easy to see from the drawing that sinus 30 degrees is equal to dB over dC. Okay, so sinus 30 degrees is 1/2, and it is equal to dB over, again, sinus 30 degrees equals to dB over BC. Repeat again, sinus 30 degrees equals to dB over BC, the hypotenuse BC. So 1/2 equals to dB over BC, but BC equals to 2 units, so we substitute BC by 2. So here we have 1/2 equals to dB over 2. Here we multiply this equation by 2, and we get that dB is equal to 1 unit. Here dB is equal to 1 unit. You continue to focus on the right triangle, triangle DBC. On the right triangle, triangle DBC, we know that cosine 30 degrees is equal to DC over BC. Okay, cosine 30 degrees is equals to DC over BC. DC is the missing side over BC. BC is equal to 2, so we substitute BC by 2. So in conclusion, we found out that cosine 30 degrees is square root of 3 over 2, and it is equal to DC over 2. Here, we'll multiply this equation by 2, and we'll get that DC equals to the square root of 3 units. DC equals to the square root of 3 units. Here, DC equals to the square root of 3 units. In the next step, we find out the size of this angle ACD. Angle ACD equals to the big angle ACB, that is equal to 75 degrees, minus the small angle DCB, that is equal to 30 degrees. So 75 degrees minus 30 degrees, it is equal to 45 degrees. Okay. In the next step, I'll copy the right triangle, triangle ADC in a new page, and we'll analyze triangle ADC. This is equals to square root of 3 units. Angle ACD equals to 45 degrees. So actually, this is the right triangle, triangle ADC that I copied from the original drawing. In triangle ADC, the sum of its angles is equal to 180 degrees, of course. So each angle here inside triangle ADC, we have this angle that is equal to 90 degrees, plus this angle that is equal to 45 degrees, plus the missing angle that will define as angle X. In total, the sum of those three angles must be equal to 180 degrees. Okay. "90 degrees plus 45 degrees equals to 135 degrees, plus X must be equal to 180 degrees. So here we subtract 135 degrees from this equation, and we get the missing angle x equals to 180 degrees minus 135 degrees is equal to 45 degrees. So this angle x equals to 45 degrees. We continue to focus on the right triangle ADC. The right triangle ADC, we have those two angles that are equal to each other. They are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. In front of this angle, we have side DC. In front of this angle, we have side AD, and those two sides, AD and DC, must be equal to each other because of the fact that they are located in front of equal angles. So DC equals to AD, but we have already found out that DC equals to the square root of 3 units. So for this equation, square root of 3 equals to DC equals to AD, we will derive that AD is also equals to square root of 3 units. Here AD equals to square root of 3 units, so we can write here that AD equals to square root of 3 units, and there also AD equals to square root of 3 units. In the next step, we will implement the Pythagoras theorem on the right triangle ADC. According to the Pythagoras theorem on the right triangle ADC, here by PT is a relation for Pythagoras theorem. The square of the aperture equals to the sum of the squares of the perpendiculars, that is to say, the square of the aperture is AC squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AD squared plus DC squared. So AD squared, AC squared must be equal to AD squared. AD is square root of 3, so AD squared is square root of 3 squared, that is 3, plus DC squared. DC squared, DC is square root of 3, therefore DC squared is square root of 3 squared, that is 3. So in conclusion, we found out that AC squared equals to 3 plus 3, that is 6. We take out of this equation number 1, and we get that AC equals to the square root of 6 units. Here we found out that AC equals to the square root of 6 units. In the next step, I will present to you a new formula in order to find out the radius of this circle. We have a new formula. Here. According to rule number 7, if we have a circle that is inscribed by triangle ABC, that could be any triangle, the radius of this circle R equals to the area of triangle ABC over the semi-perimeter of triangle ABC. The semi-perimeter of triangle ABC equals to the perimeter over 2. Okay. In this case, the semi-perimeter is A plus B plus C over 2. So we'll implement the new formula in our triangle. Here we know that according to the new formula, the radius of this circle will be equal to the area of this triangle ABC over the semi-perimeter of triangle ABC. This is the new formula. So the area of triangle ABC is equal to the base of the triangle times the height to the base over 2. and the area of triangle ABC is equal to the base. You take the base as AB, side AB, times the height to the base is DC, because it creates 90 degrees with the base, over 2. Okay, so the area of triangle ABC is AB times DC over 2. AB is equal to 1 plus square root of 3 units, times DC is equal to square root of 3 units, over 2. Okay, and 1 plus square root of 3 times square root of 3 over 2 is equal to 1.732, it is equal to 2.366 square units. So the area of triangle ABC is equal to 2.366 square units. And what is the semi-perimeter of triangle ABC? The semi-perimeter of triangle ABC equals to the perimeter over 2. And the perimeter of triangle ABC is equal to AB plus AC plus BC over 2. AB equals to 1 plus square root of 3. AC equals to square root of 6 plus BC is equal to 2. All divided by 2. And here the value of this expression, 1 plus square root of 3 plus square root of 6 plus 2 over 2, it is actually equals to 3.59 units. And the radius of the circle that is inscribed by triangle ABC equals to the area of triangle ABC over the semi-perimeter of triangle ABC, and we have already found out that the area of triangle ABC equals to 2.366 square units over the semi-perimeter of triangle ABC, that is equal to 3.59 units, and 2.366 over 3.59 is equal to 0.6589 units. So I found out that the radius of this circle that is inscribed by triangle ABC equals to 0.6589 units. We finished with the first method. In the next step, I present to you how to find out the radius of this circle that is inscribed by triangle ABC according to the second method. In the second method, we define the center of this circle as point O. We define the point of tendency of tangent BC with this circle as point D. We join points O and D together by a straight line. Point O is the center of the circle. Point D is the point of the circle itself. Therefore, OD is the radius of this circle. So we define the radius of this circle as R. Therefore, OD equals to R. And here we have the radius OD that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Rule number 1 states that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. We define we define this point as point E. Actually, it is the point of tendency of tangent AB with this circle. We define the point of tendency of tangent AC with this circle as F. We join points O and E together by a straight line. So point O is the center of the circle. Point E is the point of the circle itself. Therefore, OE is the radius of this circle that is equal to R. And again, we have here the radius OE that is bound to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle is also equals to 90 degrees. According to rule number 1, we join points O and F together by a straight line. Again, point O is the center of the circle, point F is the point of the circle itself, therefore OF is the radius of the circle, and we have the radius OF that is drawn to the point of tendency, therefore this angle equals to 90 degrees, and this angle is also equals to 90 degrees according to rule number 1. In the next step, I will present to you rule number 2. According to rule number 2, the lengths of two tangents from common external point to a circle are equal. So we have the common external point B. From the common external point B, we have tangent PA and tangent PB. And according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, PA equals to PB. Okay, we'll actually implement rule number 2 in our drawing. Well, in our drawing, we have the common external point B. From the common external point B, we have two tangents to the circle, tangent BE and tangent BD. And according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, BA is equal to BD. Likewise, we focus on the common external point C. From the common external point C, we have two tangents to the circle, tangent CD and tangent CE. And according to rule number 2, the lengths of those two tangents are equal to each other. As be equal to each other, that is to say, CD equals to CE. Okay. In the next step, we will join points O and C together by a straight line. We join points O and B together by a straight line. So here, actually, we will prove that the green triangle OBD is congruent to the orange triangle OBE. So I write it down. We'll prove that the green triangle OBD is congruent to the orange triangle OBE. So why those two triangles can go into each other? First of all, we just right now found out that side BD of the green triangle is equal to side BE of the orange triangle according to rule number 2. BD equals to BE. In addition, side DO of the green triangle is equal to side OE of the orange triangle. They are both the radii of the circle, therefore they are equal to each other. And And finally, side BO is a current side that belongs to both triangles, so side BO equals to itself. So, in conclusion, I found out that the green triangle is congruent to the orange triangle according to side rule. So we can write down that the green triangle, OBD, is congruent to the orange triangle, OBE, according to side rule. And for the fact that those two triangles congruent to each other, we conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So angle OBD in the green triangle is equal to this angle, this angle OBE in the orange triangle. So if we define this angle as alpha, angle OBE equals to alpha, then for this equation angle OBE equals to angle OBD equals to angle OBE equals to alpha, we derive that angle OBD is also equals to alpha. Angle OBD is equal to alpha. So actually those two angles are both equal to alpha, and the sum of those two angles that are alpha plus alpha, it is equal to 60 degrees according to what is given us the question. Alpha plus alpha is 2 alpha, and 2 alpha equals to 60 degrees. Here we divide this equation by 2, and we get that alpha equals to 30 degrees. Alpha equals to 30 degrees. So we can write down here that this angle equals to 30 degrees, and this angle it is also equals to 30 degrees. So here those two triangles also congruent to each other according to side rule. Therefore those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So angle FCO is equal to this angle that is actually angle OCD. Okay, angle FCO equals to angle OCD. So if we define angle OCD as theta, if this angle equals to theta, then from this equation angle FCO equals to angle OCD equals to theta, we will derive that angle FCO is also equals to theta. So both those two angles are equal to theta. So the sum of those two angles is theta plus theta. That is 2 theta, and 2 theta equals to 75 degrees according to what is given as the equation. 2 theta equals to 75 degrees. We divide the equation by 2, and we will get that theta equals to 37.5 degrees. Again, theta equals to 37.5 degrees. Okay, so in the next step we will focus on the green triangle OBD. The green triangle OBD It is very easy to see from the drawing that tangent 30 degrees is equal to OD over BD. Repeat again. And again, triangle OBD, tangent 30 degrees equals to OD over BD. OD equals to R, so we substitute OD by R over BD. So tangent 30 degrees is equal to R over BD. Tangent 30 degrees is equal to R over BD. We multiply this equation by BD and then we divide it by tangent 30 degrees and we get that BD is equal to R over tangent 30 degrees. Okay, we found out that BD is equal to R over tangent 30 degrees. In the next step, we'll focus on the right yellow triangle, triangle OCD. In the right yellow triangle, triangle OCD, it is very easy to see from the drawing that tangent 37.5 degrees is equal to OD over DC. Tangent, the yellow triangle, triangle OCD, tangent 30 degrees equals to OD over DC. OD equals to R, so we have R over DC. So in conclusion, found out that tangent 37.5 degrees equals to R over DC. Tangent 37.5 degrees equals to R over DC. So here we multiply this equation by DC and then we divide it by tangent 37.5 degrees and we'll get that DC is equal to R over tangent 37.5 degrees. Okay. Actually, we found out the values of DC and BD. And what is the value of side BC? It is very easy to see from the drawing that side BC equals to BD plus DC. Repeat again. Side BC equals to BD plus DC. So BC equals to BD, we already found out that BD equals to R over tangent 30 degrees plus DC, and we already found out that DC equals to R over tangents 37.5 degrees. Okay. We substitute BD by R over tangents 30 degrees and we substitute DC by R over tangents 37.5 degrees. In the next step, we take R as a common factor out of those two expressions and we get that R is a common factor. What is left from R over tangents 30 degrees after we took from it R is a common factor? What is left is actually 1 over tangents 30 degrees. And what is left from R over tangents 37.5 degrees after we took from it R is a common factor? What is left is actually 1 over tangents 37.5 degrees. Okay. So here R times 1 over tangents 30 degrees is equal to 1.732 plus 1 over tangents 37.5 degrees is equal to 1.303. So here we actually found out that it is equal to R times 1.732 plus 1.303 equals to 3.035 units, and here it is equal to BC, but BC equals to 2, so we substitute BC by 2. We get the 2 equals to R times 3.035. So here we divide this equation by 3.035 and we get finally that R is equal to 2 over 3.035, and this expression equals to 0.6589 units. Okay, so in both methods we found out that the radius of this circle that is inscribed by triangle ABC equals to 0.6589 units. We finished with the first question. In the next step I will present to you the second question and we will solve the second question in two different methods. So in the drawing we have rectangle ABCD. Inside rectangle ABCD we have a circle that is described by the rectangle. Chord PS equals to 6 units. Line segment SQ equals to 5 units. And our mission is to find out the area of this rectangle ABCD. So we start with the first method. Here we define side AB as A, AB equals to A. We define side BC as B, BC equals to B, and BC is also the diameter of the circle, so I'll write it down. It is very easy to see, to prove that BC is the diameter of the circle, but we will not do it now. We also know that all the angles inside a rectangle are right angles, so this angle equals to 90 degrees, this angle equals to 90 degrees, this angle equals to 90 degrees, and finally this angle is also equals to 90 degrees. Okay, we'll define the center of this circle as O. We'll join points P and O together by a straight line. Point O is the center of the circle. Point P is the point of the circle itself, therefore OP is the radius of the circle that we define as R. And we know that the diameter of the circle is equal to B. Therefore the radius must be equal half of the diameter, that is to say the radius of this circle is equal to B over 2. In the next step, I present to you a new rule, and we will implement the new rule in our drawing. According to rule number 4, the perpendicular from the center of a chord to a chord bisect the chord. So here point O is the center of the circle, here from the center of the circle the perpendicular OM, and according to rule number 4, this perpendicular OM bisects chord CD. That is to say CM equals to MD according to rule number 4. Okay, CM equals to MD. So we can implement rule number 4 in our drawing, because in our drawing we will draw from the center of the circle, that is point O, perpendicular on chord SP. So this angle equals to 90 degrees, and this angle is also equals to 90 degrees according to our construction. Okay, we define the touching point of the perpendicular from point O to chord SP as M. And according to rule number 4, the perpendicular OM bisects chord SP. If the perpendicular OM bisects chord SP, it means that SM is equal to MP. So if MP equals to X according to our definition, then from this equation SM equals to MP equals to X, we derive that SM is also equals to X. Okay? So therefore X plus X equals to SP. X plus X equals to SP. X plus X equals to SP, but according to what is given as the question, SP equals to 6 units, X plus X is 2X, that is equal to SP, that is equal to 6. From this equation, we conclude that 2X equals to 6. We divide this equation by 2, and we get that X equals to 6 over 2 is 3 units. So X equals to 3 units. Here X equals to 3 units, and here also X equals to 3 units. Okay. In the next step, we define the point of tendency of tangent DC with this circle as point F. We join points O and F together by a straight line. Point O is the center of the circle. Point F is the point of the circle itself, therefore OF is the radius of the circle, that is equal to R. According to rule number 1, we have here the radius OF that is drawn to the point of tendency. Therefore, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So inside quadrilateral OPFC we have one. So actually here we have the radius OP, that is 1 to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So inside quadrilateral OPFC, we have 1, 2, 3 right angles. Okay. Therefore, the fourth angle must be also equal to 90 degrees, because of the fact that the sum of the angles in any quadrilateral is equal to 360 degrees. So in order to complete the sum of the angles in this quadrilateral to 360 degrees, this angle must be equal to 90 degrees. So in the next step, from point Q, we draw perpendicular on BC. Again, from point Q, we draw perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle, it is also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and BC as T. We define the intersection point between the perpendicular QT and the radius OF as point L. So by this construction we created here quadrilateral OPLT. Inside quadrilateral OPLT we have 1, 2, 3 right angles. Therefore the fourth angle must be equal to 90 degrees, according to what I've already explained. So quadrilateral OPLT has 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral OPLT as a rectangle. Quadrilateral OPLT is a rectangle because it has 4 right angles. Okay. But we also know that the opposite sides of a rectangle are parallel to each other. That is to say, side OP must be parallel to side LT. OP is parallel to LT. Okay. OP is parallel to LT. But LT is part of QT. LT is part of QT, and QT is the perpendicular that we draw from point Q. So QT is a perpendicular, it is absolutely a straight line. Okay, QT is a straight line. QT is a straight line. As I already mentioned before, LT is part of the straight line QT, and LT is parallel to OP. And if a part of a straight line is parallel to OP, then the straight line QT itself must be also parallel to OP. So QT is also parallel to LT, because if a part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. Therefore QT is parallel to LT. And we have here rule number 9 that states that according to rule number 9, alternating angles between parallel lines are equal to each other. Here, line A is parallel to line B, and those two pink angles are defined as alternating angles, and they are located between the parallel lines A and B, therefore they are equal to each other according to this rule, rule number 9. We can implement rule number 9 in our drawing, because in our drawing we have OP is parallel to QT, and those two angles are defined as alternating angles that are located between the parallel lines OP and QT, therefore they are equal to each other according to rule number 9. So you can write down that angle OPM, angle OPM, this angle is equal to this angle that is actually angle PQT. I'll repeat again. Angle OPM is equal to angle PQT according to rule number 9. Okay, and if we define angle PQT as theta, if this angle equals to theta according to our definition, then from this equation angle OPM equals to angle PQT equals to theta, we will derive that angle OPM is also equals to theta. Angle OPM is also equals to theta. So here this angle is equal to theta. This angle OPM that is equal to theta. Okay. In the next step, we'll focus on quadrilateral QT DC. Inside quadrilateral QT DC, we have 1, 2, 3 right angles. Again, inside quadrilateral QT DC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. As I already explained to you, this angle must be also equal to 90 degrees. So, inside quadrilateral QT DC, we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So, we will relate to quadrilateral QT DC as a rectangle. Quadrilateral QT DC is a rectangle because it has 4 right angles. Okay. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, QT equals to DC. QT equals to DC. But ABCD is also a rectangle, and the opposite sides of rectangle ABCD are also equal to each other. That is to say, DC is equal to AB. DC is equal to AB. So here you can write down that DC equals to AB. And from this equation, QT equals to DC equals to AB, we will derive that AB is equal to DC. Okay, here AB is equal to DC. Okay, you can write here that AB is equal to DC. Okay. Actually, from this equation, QT equals to DC equals to AB, we will derive that QT is equal to AB. QT is equal to AB. Okay, here QT is equal to AB. QT is equal to AB. But according to our definition, side AB equals to A. So I can write here that side AB equals to A. And from this equation, QT equals to AB equals to A, we derive that QT is also equals to A. Okay? QT is also equals to A. In the next step, we focus on the green right triangle OPM. So I copy triangle OPM in your page and we will analyze triangle OPM. Okay. So here so actually this is the right triangle OPM that I copied from the original drawing. Here, cosine theta in triangle OPM equals to MP over OP. Okay, cosine theta equals to MP over OP. MP equals to 3 units, so we substitute MP by 3. OP equals to B over 2, we substitute OP by B over 2. So here 2 will move to the numerator, 2 times 3 is 6, and B will move to the denominator, so we get in conclusion that according to equation number 1, cosine theta is equal to 6 over B. Okay. In the next step, we'll focus on the right big triangle QPT. On the right big triangle QPT, It's very easy to see from the drawing that cosine theta equals to qt over qp. Repeat again, in the right triangle qpt, cosine theta equals to qt over qp. Qt equals to a, according to what we have already found out, so we substitute qt by a, and qp equals to 5 plus 6, that is 11. So we substitute qp by 11. So in conclusion, according to equation number 2, we actually found out that cosine theta equals to a over 11. Cosine theta equals to a over 11. So we actually have two different expressions for cosine theta. Therefore, we create equation number 3 that states that cosine theta, according to equation number 1, must be equal to cosine theta according to equation number 2. Okay? And cosine theta according to equation number 1 equals to 6 over b, and it must be equal to cosine theta according to equation number 2, that is equal to a over 11. So in conclusion, we found out that according to equation number 3, 6 over b equals to a over 11. Here we'll of course multiply this equation number 3, and we'll find out that according to equation number 3, a times b equals to 6 times 11, that is 66. So we found out that according to equation number 3, AB equals to 66. And what is the area of rectangle ABCD? The area of rectangle ABCD, it is equal to the length of the rectangle times the width. Okay, the area of rectangle ABCD equals to the length of the rectangle times the width. The length of rectangle ABCD is AB, the width is BC, AB equals to A and BC equals to B according to our definition. So in conclusion, we found out that the area of rectangle ABCD equals to AB. But we just right now found out that AB equals to 66. So AB equals to 66. So in conclusion, we found out that the area of rectangle ABCD is equal to 66 square units. So we finished in the first method. In the next step, I present to you a second way or method to find out the area of this rectangle ABCD. So here, again, we know that all the angles inside the rectangle are right angles, so this angle equals to 90 degrees, this angle equals to 90 degrees, this angle equals to 90 degrees, and this angle, it is also equals to 90 degrees. As we did in the first method, we will define side AB as A, we define side BC as B, and BC is also the diameter of the circle. We'll define the center of the circle as point O, We join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle that we will define as R. So if the radius of the circle is R and the diameter of the circle is equal to B, it means that the radius must be equal to half of it, that is to say R equals to B over 2. Here, according to rule number 1, this angle equals to 90 degrees and this angle is also equal to 90 degrees. Okay. In the next step, we'll extend the radius PO until it intersects with side AD or rectangle ABCD. And we will define the intersection point as point F. So, in rectangle ABFP, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So actually, this quadrilateral ABFP with 3 angles, therefore the fourth angle must be equal to 90 degrees. Therefore, quadrilateral ABFP must be at least a rectangle if not a square, so we'll relate quadrilateral ABFP as a rectangle. Here AB equals to A according to our definition, and we know that the opposite sides of a rectangle are equal to each other. That is to say AB equals to FP. But AB equals to A, and FP also equals to AB. Therefore, FP must be also equal to A. Okay. Likewise, in quadrilateral APDC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. We define the touching point of the extended radius PO and the circle as point T. We join points S and T together by a straight line. What is the definition of TP? Chord TP passes for the center of the circle, that is point O. Therefore, any chord that passes for the center of the circle must be the diameter of the circle. So TP is the diameter of the circle. I'll write it down. It is the diameter of the circle. And we have already found out that the diameter of the circle equals to B. Here, by joining points T and S together by a straight line, we created here peripheral angle TSP. Peripheral angle TSP rests on TP, that is the diameter of the circle. And we have also here rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of the circle must be equal to 90 degrees. So here we have the peripheral angle A and B that rests on AB, that is the diameter of the circle. Therefore, peripheral angle A and B must be equal to 90 degrees according to this rule, rule number 5. We can implement rule number 5 in our drawing because we have in our drawing peripheral angle TSP that rests on TP, that is the diameter of the circle. Therefore, peripheral angle TSP, this angle must be equal to 90 degrees according to rule number 5. We define this angle as theta. So if we focus on triangle TSP, this angle equals to 90 degrees. This angle equals to theta, so this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in any triangle. So if you focus on the right triangle QFP, this angle equals to theta, this angle equals to 90 degrees. Therefore, this angle must be equal to 90 degrees minus theta, exactly for the same reason that this angle must be equal to 90 degrees minus theta. So in the next step, we'll prove that the green right triangle, triangle TSP, is congruent, is similar to the big right triangle FQP. So I write it down. We'll prove that the big right triangle FQP is similar to the small green triangle TSP. So why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So here, angle QFP is equal to this angle, that is actually angle TSP. Here, angle QFP, the big right triangle, equals to angle TSP, the green triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So this angle, it is actually angle FQP. Is equal to this angle, that is actually angle STP. Repeat again. Angle FQP, the big right triangle, is equal to angle STP, the green triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. And finally, this angle theta is a common angle that belongs to both triangles, so angle theta equals to itself. Okay, so angle FPQ, that is angle theta, is equal to itself. You can call it to angle theta, also angle TPS. Two different names to the same angle theta. Repeat again. Angle theta, that is angle FPQ, equals to angle theta, that is angle TPS. Angle theta is a common angle, therefore angle theta equals to itself. So actually prove that the big right triangle FQP is similar to the small right triangle TSP, according to angle similarity rule. So I write it down. Angle triangle FQP is similar to triangle TSP, according to angle similarity rule. And from the fact that the green triangle is similar to the big right triangle, we derive that the following relationship exists between their sides. We conclude that FP over SP is equal to QP over TP. Repeat again, we conclude that FP over SP equals to QP over TP. FP equals to A, so we substitute FP by A over SP equals to 6 units, according to what is given as the question, and it is equal to QP. What is the value of QP? QP equals to 5 plus 6, that is 11. So QP is 11 over TP. What is the value of TP? TP is the diameter of the circle, that is equal to B. So in conclusion, according to equation number 1, we found out that A over 6 equals to 11 over B. Here we cross multiply this equation, equation number 1, and we'll get that according to equation number 1, A times B equals to 6 times 11, that is 66. So AB equals to 66, and what is the area of rectangle ABCD? The area of rectangle ABCD equals to the length of the rectangle, that is AB, times the width, that is BC. The length is A, and the width BC is B, according to our definition. So found out that A and the area of rectangle ABCD is AB, but according to equation 1, AB equals to 66. So in conclusion, found out that the area of rectangle ABCD is equal to 66 square units. Okay, we finished with the second method. In the next step, I summarize the lecture. We start with the first question, of course. So, in the drawing, we have triangle ABC. Inside triangle ABC, we have this circle that is inscribed on triangle ABC. Side BC equals to 2 units. Angle ABC equals to 60 degrees. Angle ACB equals to 75 degrees. And our mission is to find out the radius of the circle that is inscribed by triangle ABC. Okay, so in the first method, from point C, we draw perpendicular on AB. In this way, we create the triangle BDC. I copy the great triangle BDC in the new page, and we analyze triangle BDC. So here, this is triangle BDC. This is a copy from the original drawing. What is the sum of what is the angles inside triangle BDC? We have this angle that is equal to 90 degrees. This angle equals to 60 degrees. Plus the missing angle that we define as x. In total, the sum of those two angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. 90 degrees plus 60 degrees is 150 degrees, and 150 degrees plus x must be equal to 180 degrees. We subtracted 150 degrees from this equation and found out that the missing angle x equals to 180 degrees minus 150 degrees is 30 degrees. So if this angle equals to 30 degrees, and this angle equals to 30 degrees. We continue to focus on triangle BDC. In triangle BDC, it is very easy to see that sinus 30 degrees equals to BD over BC. Sinus 30 degrees equals to BD over BC. So sinus 30 degrees is 1/2 over it, and it is equal to BD over BC, but BC is 2, so we substitute BC by 2. We got that 1/2 equals to BD over 2. We multiply this equation by 2, and we found out that BD equals to 1. Here, BD equals to 1. Continue to focus on triangle BDC. In triangle BDC, cosine 30 degrees equals to DC over BC. Cosine 30 degrees is square root of 3 over 2, and it is equal to DC over BC. BC is 2, so we substitute BC by 2, and we found out in conclusion that square root of 3 over 2 equals to DC over 2. We multiply this equation by 2, and found out that here DC equals to square root of 3 units. Here, DC equals to square root of 3 units. Then, what is the size of this angle? Angle ACD is equal to the big angle, that's angle ACB, that is equal to 75 degrees, minus the small angle, angle DCB, that is equal to 30 degrees. Therefore, this angle will be equal to the big angle, that is 75 degrees, minus the small angle, that is 30 degrees. 75 degrees minus 30 degrees, this is 45 degrees. So this angle equals to 45 degrees. Then I copied the right triangle ADC in the new page, and we analyze triangle ADC. Here, this is triangle ADC that I copied from the original drawing. So, the sum of the angles inside triangle ADC must be equal to 180 degrees. Which angles we have here? This angle equals to 90 degrees. This angle equals to 45 degrees. this is the missing angle that we define as x. In total, the sum of the three angles must be equal to 180 degrees. So 90 degrees plus 45 degrees is 135 degrees, and 135 degrees plus x must be equal to 180 degrees. We subtracted 135 degrees from this equation. We found out that the missing angle x equals to 180 degrees minus 135 degrees. It is equal to 45 degrees. So this angle equals to 45 degrees. So those two angles are equal to each other. And we have the rule that in front of equal angles in the triangle there are equal sides. So in front of this angle we have side DC. In front of this angle we have side AD. And those two sides must be equal to each other because of the fact that they are located in front of equal angles. So side DC equals to side AD. But we have already found out that DC equals to square root of 3. So from this equation, square root of 3 equals to DC equals to AD, we derive that AD equals to square root of 3 units. AD equals to square root of 3 units. So here you can write down that AD equals to square root of 3 units. Then we implemented the Pythagoras theorem on this right triangle, triangle ADC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to AD square plus DC square. So AC square equals to AD square. AD is equal to 3, so AD square is equal to 3 square, that is 3. DC equals to square root of 3, so DC square is equal to 3 square, that is also 3. So in conclusion, found out that AC square equals to 3 plus 3, that is 6. We took out of this equation number 1, and found out that AC equals to square root of 6 units. AC equals to square root of 6 units. Then I presented to you rule number 5. According to rule number 5, the radius of any circle that is inscribed by a triangle will be equal to the area of the triangle that blocks the circle over the semi-perimeter of the triangle. So we implemented this new rule in our triangle in order to find out the radius of this circle, and according to the new formula, the radius of this circle will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC. And the semi-perimeter of any triangle is the perimeter over 2. So what is the area of triangle ABC? It will be equal to the base of the triangle times the height over 2. We took the base as AB, and the height to the base is DC. So it is AB times DC over 2. AB equals to 1 plus square root of 5. The height DC equals to square root of 3 over 2. So this expression equals to 2.366 square units. So the area of triangle ABC equals to 2.366 square units. Then we calculated the semi-perimeter of triangle ABC. The semi-perimeter of triangle ABC equals to the perimeter of the triangle over 2. The perimeter of triangle ABC is AB plus AC plus BC. That is the sum of its side lengths over 2. AB equals to 1 plus square root of 3, AC equals to square root of 6, BC equals to 2. If we divide it by 2, we get the semi-perimeter. So this expression equals in total to 3.59 units. That is to say, the semi-perimeter of triangle ABC is 3.59 units. Therefore, the radius of this circle that is inscribed by triangle ABC equals to the area of triangle ABC, that is 2.366, over the semi-perimeter of triangle ABC, that is 3.59 units. So 2.366 over 3.59 is 0.6589 units. So the radius of this circle, it is equal to 0.6589 units. We finished with the first method. Then I presented to you how to find out the radius of the circle that is inscribed by triangle ABC according to the second method. In the second method, we define the center of the circle as point O. We define the intersection point of side BC or tangent BC with the circle as point D. We join points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of the circle that we defined as R. Okay, we define the point of tendency of tangent AB with this circle as point E. Point O is the center of the circle, point E is the point of the circle itself, therefore O is the radius of the circle that is equal to R. So here we have the radius OE that is drawn to the point of tendency, therefore this angle equals to 90 degrees, this angle also equals to 90 degrees according to rule number 1. Likewise, we have the radius OD that is drawn to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. We join points O and F together by certain point O is the center of the circle, point F is the point of the circle itself, therefore OF is the radius of the circle that is equal to R. So we have the radius OF that is drawn to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Then I presented to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point P. From point P we have tangent PA and tangent PB. According to rule number 2, the lengths of the two tangents are equal to each other. That is to say, PA equals to PB. We implemented rule number 2 in our drawing. If we focus on the common external point B, from the common external point B we have two tangents to the circle, tangent BE and tangent BD. And according to rule number 2, they must be equal to each other, that is to say BD equals to BE. Likewise, we focus on the common external point C. From the common external point C, we have two tangents to the circle, tangent CD and tangent DF. And according to rule number 2, they must be equal to each other, that is to say DC equals to CF. Then we proved that the green triangle is congruent to the orange triangle according to side rule. I will explain what I mean here. Side BD of the green triangle equals to side EB of the orange triangle according to rule number 2. Side DO equals to side OE, they are both the radii of the circle, therefore they are equal to each other. And finally, BO equals to itself, it is a common side that belongs to both triangles, so we actually proved that the green triangle is congruent to the orange triangle according to side rule. And from the fact that those two triangles congruent to each other, we will conclude that those two angles must be equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. That is to say, side OB equals to side OBD equals to side OBF. So if we define one angle as alpha, then the other angle must be also equal to alpha. So those two angles, they are both equal to alpha. And alpha plus alpha equals to 60 degrees according to what is given as the equation. That is to say, alpha plus alpha is to alpha, that is equal to 60 degrees. We divided this equation by 2 and found out that the missing angle alpha equals to 30 degrees. So this angle equals to 30 degrees and this angle also equals to 30 degrees according to what we have already found. So here, then we actually can prove easily that those two triangles are also congruent to each other according to side rule. Therefore, those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So, if we define, so here we can write down that angle FCO equals to angle OCD. So, if we define one angle is theta, if this angle equals to theta, then the other angle must be also equal to theta. So, both those two angles are equal to theta, and theta plus theta equals to 75 degrees according to what is given as the equation. So, theta plus theta is 2 theta, that is equal to 75 degrees. We divided this equation by 2 and found out that angle theta equals to 37.5 degrees. Then we focused on the green triangle OBD. The green triangle OBD tangents 30 degrees equals to OD over DB. Tangents 30 degrees equals to OD over BD. OD equals to R. So tangents 30 degrees equals to R over BD. We multiply this equation by BD and then we divided by tangents 30 degrees and found out that BD equals to R over tangents 30 degrees. Likewise, we focused on the yellow triangle ODC. The yellow triangle ODC tangents 37.5 degrees equals to OD over DC. Okay, repeat again, tangents 37.5 degrees in the yellow triangle ODC equals to OD over DC. OD equals to R, is R over DC. So tangent 37.5 degrees equals to R over DC. We multiply this equation by DC and then we divide it by tangent 37.5 degrees, and therefore we found out that DC equals to R over tangent 37.5 degrees. Okay, so we have actually the values of BD and DC. And what is the value of the length of BC? It is very easy to see from the drawing that BC equals to BD plus DC. Here BC equals to BD plus DC. BD equals to R over tangent 30 degrees. DC equals to R over tangent 37.5 degrees. So here we took R as a common factor. And what is left from this equation, from this expression after we took from it R as a common factor, what is left is actually R over tangent 30 degrees. What is left from R over tangent 37.5 degrees after we took from it R as a common factor? What is left is actually 1 over tangent 37.5 degrees. 1 over tangent 30 degrees equals to 1.732. 1 over tangent 37.5 degrees equals to 1.303. And if we add those two numbers with each other, we get that they are equal to 3.035. So 2 equals to R times 3.035. We divided this equation by 3.035, and we got that the radius of this circle, of the circle that is described by triangle ABC, equals to 2 over 3.035. That is equal to 0.6589. So in both methods we found out that the radius of this circle that is described by triangle ABC equals to 0.6589 units. We finished with the first question, then I presented you the second question, and we solved the second question in two different methods. So in the drawing we have a rectangle. Inside this rectangle we have this circle that is described as the rectangle, called PS equals to 6 units, line segment SQ equals to 5 units, and our mission is to find out the area of this rectangle ABCD. Okay, so here we know that all the angles inside the rectangle are right angles. Those 4 angles are right angles. We define AB as A, we define BC as B, and the diameter of this circle, it is also equals to BC. So here we write down that the diameter equals to B. We define the center of the circle as O. We join points O and P together by a straight line. Point O is the center of the circle. Point P is the point of the circle itself. Therefore, OP is the radius of the circle that we defined as R. And so, if the diameter of the circle is B, then the radius must be equal to half of it, that is B over 2. So R equals to B over 2. Okay? Then, I presented to you rule number 4, and we implemented rule number 4 in our drawing. According to rule number 4, if you draw from the center of the circle perpendicular to any chord, it bisects that chord. So for point O, we draw perpendicular to chord SP, that is perpendicular OM. Perpendicular OM, according to rule number 4, bisects chord SP. That is to say, according to rule number 4, SM equals to MP. SM equals to MP. So if we define MP as X, then from this equation SM equals to MP equals to X, we derive that if we define MP as X, then SM equals to MP equals to X, then from this equation SM equals to MP equals to X, we derive that SM is also equals to X. Okay? So, therefore, X plus X equals to SP. X plus X equals to SP, but SP equals to 6 according to what is given as the equation. X plus X is 2X, so 2X equals to SP equals to 6. From this equation we derive that 2X equals to 6. We divided this equation by 2 and found out that X equals to 3 units. Here X equals to 3, X equals to 3. Then actually we defined the point of tendency with this circle as F. We join points O and F together by a straight line. Point O is the center of the circle, point F is the point of the circle itself, therefore OF is the radius of this circle that is equal to R. The radius of OF it is drawn to the point of tendency, therefore this angle equals to 90 degrees, this angle also equals to 90 degrees. Here the radius of P is drawn to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees. So actually we created here quadrilateral OPFC, inside quadrilateral OPFC we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. In order to complete the sum of the angles in this quadrilateral to 360 degrees, this angle must be equal to 90 degrees. Okay? Then from point Q we draw perpendicular on BC. Define the touching point of the perpendicular from point Q and BC as T. And here actually so this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. So inside quadrilateral OPLT we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. Therefore inside quadrilateral OPLT we have 4 right angles, and any quadrilateral that does 4 right angles must be at least a rectangle if not a square. So quadrilateral OPLT is a rectangle. Here quadrilateral OPLT is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say OP equals to LT. The opposite sides of a rectangle are parallel to each other. Therefore OP is parallel to LT. OP is parallel to LT. But LT is part of the perpendicular QT. LT is part of the perpendicular QT. QT is a perpendicular, it is absolutely a straight line. Here, QT is a perpendicular, it is absolutely a straight line. So here, so we have here part of the straight line QT, that is to say LT, is parallel to OP. So if part of the straight line QT is parallel to OP, therefore the straight line QT itself must be also parallel to OP. Okay, here the straight line QT must be also parallel to LT. Why? Because if a part of the straight line is parallel to another straight line, then if a part of a straight line is parallel to another straight line, then the straight line itself, that is to say QT, must be also parallel to the other straight line, that is OP. Therefore QT is parallel to OP actually. Here QT, okay, here OP is parallel to LT, it is the same. Here we can write down that LT is parallel to OP. Okay, LT is parallel to OP. And then I presented to you rule number 9, that alternating angles between parallel lines are equal to each other. Those two angles are defined as alternating angles and they are located between the parallel lines OP and QT, therefore they are equal to each other according to rule number 9. Okay, that is to say angle MPO equals to angle PQT. So if we define angle PQT as theta, then from this equation angle MPO equals to angle PQT equals to theta, we derive that angle OPM is also equals to theta. This angle is also equals to theta. Then we focused on the right triangle on quadrilateral QDTC inside quadrilateral QTCD. We have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Therefore in quadrilateral QTCD we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral QTDC as a rectangle. Quadrilateral QTDC is a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say QT equals to DC. QT equals to DC, but DC is part of rectangle ABCD. And we know that ABCD is a rectangle, so the opposite sides of rectangle ABCD must be equal to each other. That is to say, DC must be equal to AB. So here, DC equals to AB. And from this equation, QT equals to DC equals to AB, we will derive that QT is also equal to AB. QT is also equal to AB. But according to our definition, AB equals to A. So from this equation, QT equals to AB equals to A, we will derive that QT is also equals to A. Okay? So here QT is also equals to A. Then I copied the right green triangle, triangle OPM in a new page, and we analyze triangle OPM. In triangle OPM, we have OP equals to B over 2, MP equals to 3, this is angle theta. So cosine theta in triangle OPM equals to MP over OP. Again, cosine theta equals to MP over OP. MP equals to 3, OP equals to B over 2, 3 over B over 2 equals to 6 over B. So in conclusion, we found out that according to equation number 1, cosine theta equals to 6 over B. Then we focus on the right big triangle, triangle QPT. In the right big triangle, triangle QPT, cosine theta equals to QT over QP. In the right big triangle, triangle QPT, cosine theta equals to QT over QP. QT equals to A according to what we already found out. So we substitute QT by A. What is the value of QP? It is very easy to see from the drawing that QP equals to 5 plus 6, that is 11. So we substitute QP by 11. So in conclusion, we found out that according to equation number 2, cosine theta equals to A over 11. So we have two different expressions for cosine theta. Therefore, we created equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. Cosine theta according to equation number 1 equals to 6 over B, and cosine theta, and it must be equal to cosine theta according to equation number 2, that is equal to A over 11. So in conclusion, we found out that according to equation number 3, 6 over 3, 6 over B equals to A over 11. We of course multiply this equation number 3, and we found out that AB equals to 66. AB equals to 66, and what is the area of rectangle ABCD? The area of rectangle ABCD equals to the length of the rectangle times the width of the rectangle. The length of the rectangle is AB, the width is BC. AB equals to A and BC equals to B according to our definition. So in conclusion, we found out that the area of triangle ABC equals to AB, but according to what we just right now found out, that AB equals to 66, here AB equals to 66, so in conclusion we found out that the area of rectangle ABCD equals to 66 square units. So we finished with the first method, and I presented to you a second method to find out the area of rectangle ABCD. Again, we know that all the angles inside a rectangle are right angles. So those 4 angles, they are all right angles. We defined, as we did in the first method, AB as A, BC as B. And I already explained to you that VC is also the diameter of the circle, so we can write down that VC equals to V equals to the diameter of the circle. We define the center of the circle as O. We join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle that we defined as R. We know that the diameter of the circle equals to B. Therefore, the radius must be equal to half of it, that is B over 2. So the radius of the circle equals to B over 2. Then according to rule number 1, the radius OP is drawn to the point of tendency, and therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay, then we actually extended the radius of PO until it touches side AD of rectangle ABCD at point F. Okay, and here we defined actually inside quadrilateral ABFP, inside this quadrilateral we have 1, 2, 3 right angles. Therefore the fourth angle, this is the fourth angle, it is also must be equal to 90 degrees. So quadrilateral ABFP is 4 right angles, therefore quadrilateral ABFP must be at least a rectangle if not a square, so we relate for quadrilateral ABFP is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say AB equals to FP, but AB equals to A according to our definition, therefore FP that is equal to AB must be also equal to A. Okay, then we define the touching point of the extended radius PO and the circle as T. What is the definition of chord TP? Chord TP passes through the center of the circle, therefore it must be the diameter of the circle, because any chord that passes through the center of the circle must be the diameter of the circle, therefore TP is the diameter of the circle that is equal to B. Then we join points T and S together by a straight line. In this way we created peripheral angle TSP that rests on TP, that is the diameter of the circle. And any peripheral angle that rests on the diameter of the circle must be equal to 90 degrees, therefore according to rule number 5, this angle, peripheral angle TSP that rests on the diameter must be equal to 90 degrees. Okay, so we defined this angle as theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in the entire. Likewise, according to the same reason, this angle equals to 90 degrees. This angle equals to theta in the big right angle Q of P. This angle equals to 90 degrees. This angle equals to theta, therefore this angle must be equal to 90 degrees minus theta. Then we prove that the green right angle is similar to the big right angle FQP. Why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, both those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. And finally, angle theta is a common angle that belongs to both triangles, so angle theta equal to itself. So we actually proved that those two triangles are similar to each other according to angle similarity rule. And from the fact that those two triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that FP over SP equals to QT, FP over SP equals to QP over TP. Okay, FP equals to A, so we substitute FP by A. SP equals to 6, so we substitute SP by 6. QP equals to 5 plus 6, that is 11, therefore we substitute QP by 11. And finally, TP is the diameter of the circle that is equal to B, therefore we substitute TP by B. So in conclusion, we found out that according to equation number 1, A over 6 equals to 11 over B. We cross multiplied this equation number 1, and found out that A times B equals to 66. Okay. And what is the area of rectangle ABCD? The area of rectangle ABCD equals to the length of the rectangle, that is AB, times the width of the rectangle, that is BC. AB equals to A and BC equals to B according to our definition. Therefore, we found out that the area of rectangle ABCD equals to A times B. But we just right now found out that according to equation number 1, A times B equals to 66. So we can write here that AB equals to 66, and finally, in conclusion, found out that the area of rectangle ABCD equals to 66 square units. So in both methods, we found out that the area of rectangle ABCD equals to 66 square units. And likewise, in the first question, here in both methods, we found out that the radius of this circle that is inscribed by this triangle ABC, it is equal to 0.6589 units. Okay, thank you very much.